can also use the mouse.
No, it's okay. Okay, can I go? Okay. Well, thank you, and thank you for everybody staying for the last session. So this presentation mainly involves the graduate work of Magdi Maraki and Nicholas Kowalski, and it's related to looking at how we can model vehicle mobility in off-road environments in an efficient way. Well, I will talk about this later. So really the main objective is vehicle mobility. And if you think about vehicles, your main interest is rigid body motion, translation, and potentially rotation. Of course, deformation is important, but you don't really think about how your tires are deforming. You just want to essentially, let's say, translate and rotate. And in off-road environment, this is really, really critical. So the key behavior, what here we address is wheel obstacle or vehicle obstacle negotiation. That's one of the, let's say, the canonical problems that in off-road locomotion people are looking at. The other is locomotional soft soil, what I will not address here. That's another presentation. So again, what we want is to achieve essentially interactive race real-time simulation. So we can also use this in training simulators, digital twins, or whatever we wanna call those. And we want to model, use as much as possible rigid body models, both for, let's say, for the articulated body system and both for the collision geometries, but still include the effect of deformation, specifically wheel deformation where the wheels are contacting obstacles. And also through this, quantify the ability of a vehicle in a parametric form, so I can design the suspension, design the various elements to maximize, for example, the capability to climb obstacles. So if we go further, so one motivating aspect, of course, there can be many, but in our case, in the past years when we started to work was space exploration, but like probably everybody knows, space really is depending on the availability of funding. So nowadays, it really came back also. Canada is building the Canadian Lunar Utility Vehicle, where of course the locomotion capability, the mobility is really influenced by how the wheels are interacting with the terrain, both in soft soil environments and also negotiating obstacles. But what I will present essentially in the past years, we also use this, of course, for many terrestrial applications. We don't necessarily have to go to space to have off-road environments. So a large part of this work relates to essentially how I can simplify the representation of wheels. And of course, if I look at a full wheel, there can be all kinds of models, on parameter, finite element models. But what we want is essentially, eventually we want to model this wheel as a rigid body as much as possible, but represent the contact force systems acting on it so they account for the effect of wheel deformation. Here I will particularly address obstacle negotiation, but for example, in the case of locomotion on soft soil or even on hard terrain, this comes down essentially to the contact patch. How I can account for the contact patch size when the wheel flexibility, deformability changes, because that greatly influences the traction capabilities of the wheel. The core element, what I will illustrate it with a very simple example. So if I think about I just think about single one-dimensional motion for two, could be spheres, could be any other elements just in translation. The contact force between the two, which is like Fc here, is really developing power related to the relative motion. So what I want somehow to isolate this so I can understand how the system parameters are affecting that. So of course, it's a very simple way to write dynamic equations in global coordinates, but these do not isolate a single equation that would represent the dynamics associated with the contact here. If I do coordinate transformation, of course, I can use relative coordinates and so on. You can try, the system remains coupled. So what really decouples this is a so-called mass orthogonal decomposition, which actually gives rise, of course, this is just the relative velocity here associated with, let's say, the contact force. And another component, what I like to call admissible velocity, which is kinematic in, let's say, nature, but it's not kinematically intuitive. So it's related to mass ratios. And if I use this transformation, basically my mass matrix will be decoupled. I can isolate an equation directly associated with the contact dynamics. I have effective mass centering. We can do the same thing for stiffness. So then, of course, I would have effective stiffness terms. And it also decouples the kinetic energy. So there is one part of the kinetic energy dominated by the effective mass, which is basically responsible for the contact dynamics. And then another part, which is the admissible part, and the related generalized momentum associated with the admissible motion, that represents what energy stays in the system after contact. Of course, if I look at impact, contact onset, there are two phases. One which I can characterize as a compression. That's when all of this so-called constrained kinetic energy basically dissipated. And if there is restitution, it is recovered. If not, then it just stays in the system in a potentially unmodeled form. So this is the main idea, basically, to use the constraint and also the admissible to come up with a reduced model. Then I can capture basically the dynamics for a more complex system. Let's say a system with arbitrary number of degrees of freedom to develop parametric function. We can see here that this is parametric function of the system parameters. And this can be shown, I will show it here also later, but we did variety of tests and experiment. This is directly proportional to the contact force. So it gives an alternative measure, a measure alternative to the contact force, which depends on the system parameter. I set here the extension for an arbitrary system is straightforward. The reason is, well, of course, there's a lot of projections, math involved, but at the velocity level, the dynamics the kinematics is linear. So I can basically use tools from linear algebra and so on. So this is really the core aspect. There are other equations here, but I think this hopefully demonstrates it. So the main element, then what we do, we use a rigid body model for the wheel, both for the dynamics and also the contact geometry. The contact geometry is very important because basically using, let's say, rigid body primitives for contact detection can be done much more efficiently as opposed to if we were using a deformable mesh, for example. So initially, we let the wheel contact the obstacle. Then at that point, we determine the characteristic direction which we associate with the, let's say, the contact force or the main effects of the contact force. We determine the related kinetic energy part. Based on then, considering an effective stiffness, what we determined before, we determine a characteristic deformation. Then we let the wheel go, and basically using this characteristic deformation, we reposition the contact points in order for the contact force system to be able to develop the effect what we are expecting from the wheel deforming. So this is essentially the main thing. So here I just, again, equations for representing physically the same sort of thing. Again, projecting in a case of more degrees of freedom, of course, I have to do that to determine the related kinetic energy part and so on. And this is what kind of captures a little bit graphically what I mentioned. So we equate essentially this constant kinetic energy with a maximum deformation. We are assuming a linearly elastic behavior, and the effective stiffness can come in various ways. I will show results later. This came, in that case, discretizing a tire in the F-tire environment, which is probably the primary package to model tires, could come from experiments and so on. And then essentially what we do at this point, there is a little bit of radius actually to this. It's not completely sharp, but the characteristic direction with the contact is this. So we determine that, we let the wheel go further, and we reposition the contact point here. So this really selecting the proper contact point location, which will make sure that the force system developed due to the deformation of the wheel will have that's what the expected effect on the overall rigid body motion of the wheel. And then we let the simulation go further. And then essentially, in that case, I sort of represented to some extent the contact force through this constraint kinetic energy. But what remains in the system is the momentum associated with the admissible motion that will decide essentially whether the wheel can climb or not. So if I go further, and yes, these are the tests. So we had a bit over 1,000 test results for a certain wheel under pneumatic wheel under different tire pressures. This was conducted by one of our industrial partners using the F-tire environment. So based on this, we had an idea about the effective stiffness behavior of the wheel. And then again, what we did, then we did two simulations. One in the F-tire environment, the fully flexible, completely independent simulation, looking at how the wheel can climb or negotiate the obstacle. And the other is with our rigid wheel model, but considering what we call the deformation-aware contact geometry or contact considerations. And then there was a number of course, obstacle height, initial velocity, inflation, pressure, and so on. So we can see here the simple MATLAB illustration. These two represent the same wheel. But first is a rigid body model where I don't consider basically deformation at all, so it bounces back. When I consider deformation, you can see a little bit. The penetration here is essentially represents the deformability of the wheel. It climbs over, and this is, I guess, it's maybe it's a common, let's say, intuition also that of course, if you add a little bit of flexibility to the wheel, you can increase the capability to climb. So again, for a single wheel test, we did a bit over 1,000 different comparisons with the F-tire fully flexible, completely independent simulation. So the agreement was around 74%. So when the disagreement was found, the F-tire simulation seemed to be a bit unstable, maybe unreliable, when the velocities were higher and the obstacle height with respect to the wheel diameter was higher also. So we are investigating this also now experimentally, but we found that it's probably a reasonable agreement considering that the two were completely independent simulations. So this, let's say, simplified model was also in Vertex Studio is the environment of one of our industrial partners, CMLab simulations. It's a multi-body dynamics environment. So we implemented this also considering, say, there is a rigid wheel contact and also this, let's say, deformation-aware contact geometry approach. So this is a full vehicle simulation. Hopefully it's visible. One is, again, is the same, but the deformation-aware is able to negotiate the obstacle, while if I don't consider the wheel deformation, of course, it's well, not necessarily, of course, but in this case, it bounces back. So we went further and we built a little, we call it a rover prototype. That's why I showed the space motivation aspect, because this most resembles like a rover, not necessarily a car or a larger vehicle, what I just showed. And we have the experimental platform, which is, well, no, let me go back. I will show it later. But we constructed a model of this. And also what we did, though this doesn't show completely, this shows like some arbitrary wheels. We also built a variety of deformable wheels. Not pneumatic, essentially these can undergo, but solid wheels. So again, we did all these considerations for determining the constraint kinetic energy measure for the entire system. This is everything is considered in this, not just the wheel. And we can see here the rover prototype and one of the experiments where it impacts an obstacle. And again, the intention here, eventually the intention is this experimental evaluation is still ongoing, is to really prove that as a measure, we could develop this parametric form to characterize the ability. But here we particularly looked for whether we are able to match based on our model to determine the constraint kinetic energy measure and the deformation, what we can evaluate based on camera measurements, we are able to sort of make an equivalence with those. So these three rover configurations considered, again, as I said, this parametric measure really depends on the geometric dimensions, mass distribution. If there is control parameters that can also be included. So really the geometry, the configuration of the system is governing how, let's say, severe the wheel impact with the obstacle would be. So these are the three configurations we considered. And then the test, again, this is ongoing, but currently the tests are really showing that there is an agreement I have the more constant kinetic energy, I'll evaluate based on the model, and what I measure deformation is really corresponding to that. But eventually, this is something what we want to more generalize, so we can really say for various wheel sizes, various mechanical designs, that this is a viable form, and I don't necessarily have to measure the contact force in order to have this, let's say, ability built in the rover system itself to be able to essentially maximize the obstacle negotiating capability, so the mobility on rough terrains. So, and then the conclusion is essentially that what the intention was is to develop what we term the reduced model, which can be used together with rigid body simulations. And we are able to solve this real-time, what I showed, multi-body simulations. Those are actually real-time simulations. And then still consider the deformation of the wheels when the wheel is impacting various objects. And through that also to develop a parametric measure that can be used either for the control or the design of the mechanical structure, mechanical system of a vehicle. So thank you very much. We also have our group here.
I would have a question for curiosity, which is semi-related. And this is if I would go to the desert, right? So to a ground which is completely different, no obstacles, but sand. How would I treat this in this framework?
So that's why I brought up also the space exploration, because for space exploration, when they design a rover or develop one, there are two main tests. One test is that you have to drive the rover, say, and one of the wheels that is negotiating an obstacle of a certain size. So this work more relates to that. The other test, when I drive the rover on a certain slope, flat slope, but soft soil. So if I think about a desert environment, that's more. So we have a lot of, yes. So this specifically, this is only addressing the obstacle negotiating. When the wheel is impacting an obstacle and how I would do that, how I can, say, maximize mobility for that case. The other aspect, we have been working quite a bit on that, on the soft soil modeling, but this is not a soft soil. So this as is, you really need a hard obstacle essentially to apply this. But these two, maybe not in the desert, but in various environments, these two come combined essentially. You have soft soil and you have also hard obstacles. Yeah, thank you. Okay.
Yeah, we have the microphone here.
Okay. So, good afternoon. It's a pleasure to be here. My name is Ricardo. I come from the University of Porto, the Faculty of Engineering, and this work was developed with my colleagues and supervisors. And our work is named Surface Pattern Design using the boundary element method and Bayesian optimization. So first, a quick motivation for our work. We were highly inspired by this work developed by Antoine Aymar and the colleagues that is named Designing Meta-Interfaces with Specified Friction Loss. And basically, for having the same surface to have different friction behaviors, they needed to control, have different relationships between pressure and contact area. And to do so, they used a PDMES square lattice with 64 asperities, uniformly distributed in a 20 by 20 millimeter grid, and with 3 levels of asperities. So by controlling the height of the asperity, the number of asperities, they could control this relationship. So these are the analytical equations that rule the relationship. So these are obtained using the Earth's theory and considering each microcontact as independent. And the sequential design strategy developed by the authors considered So we have our first target point. We define the height of this first level, and then we use the equations to compute the number of asperities and the position of the plane. Then we have to trim our n value because it's a real value and we want an integer. And by doing so, we have to add a new asperity to reach the desired point. So we keep doing this and we set the height of the next level equal to the position of the plane from the previous one. And by doing this, we guarantee that we are not interfering with the previous results. Okay, so the question that arises from this framework, at least in our group, is what can we extend this design of meta interfaces to a computational framework? And with this work, that is a very recent work, we try to start answering this question. So we developed a numerical strategy for this. So we need a numerical solver to perform contact simulations, and we need a big optimization tool to do the optimization of our responses. So for the numerical simulation, we use the very well-known in our community boundary element method code, the CMIS, and for optimization, we used Piglet, that is an in-house optimization tool that is highly specified for Bayesian optimization. So I'm not by any means a specialist in Bayesian optimization, but I will try to give a quick overview. So we have an objective function, we sample some random points, and we build a Gaussian process, a probabilistic model for our objective function. So then we take this probabilistic model and we use acquisition functions such as the upper confidence bound and expected improvement. And we try to optimize these functions by finding the maximum value. And with this, we compute the next candidates and we evaluate once again our objective function. And we keep doing this until reaching the maximum number of iterations or the convergence tolerance. This is a very well-known method for expensive evaluations with no gradient available. So for black box functions, it works very well. And in our group, we tried to focus on a slightly different version of the Bayesian optimization. So instead of only looking at the final scalar loss, we tried to look at the whole numerical simulation. So instead of building the Gaussian process at the level of the loss, we build the Gaussian process at the level of numerical simulation. For example, in our case, as we were trying to do a curve fitting, so we have some target points, and we are trying that our numerical simulation fit these target points, we, instead of building the Gaussian process only in the mean square error loss, we build the Gaussian process on considering each error between our response and the reference response. And by doing so, we can observe the entire response, which leads to less entropy when computing the objective value, and our model does not need to learn the reduction function, which increases the predicting ability. Okay, so considering this, we built some optimization strategies. So the first one is very similar to the one developed by the authors of the paper that I mentioned. So we have one target point. We try to optimize the number of asperities for that target point. We evaluate using numerical simulations that candidate, and then we check for convergence. And then we set, if we get the desired loss, we set the height of the next target point equal to the position of the previous plane. Then we propose a slightly different version where we have also the height of that level as a variable to optimize, and a more general optimization strategy that is a simultaneous strategy where we try to optimize everything at once. Okay, so in the first one we have only 2 or 3 variables per optimization, and the second one we have 6 variables per optimization. Okay, so here we have some results. First of all, instead of using the numerical solver, we started by using the analytical solution. We have here our optimization setup. We use composite Bayesian optimization, 256 iterations, and a loss tolerance 10 to the power of -6. Here are the bounds of our parameters for the sequential fixed heights, here for the sequential free heights, and here for the simultaneous optimization framework. Okay, here we have our results. So in blue are the target points, in red the sequential with the fixed height, in green the sequential with the free height, and in yellow the simultaneous optimization results. We can see that all the optimization strategies were able to pass in the target points. However, the response are really different from each other. And we can see that in detail in this graph where we have the height error, that is basically a relative error of our heights comparing to the results from the paper. And we can see when we use a similar strategy, we have almost the same heights, but as we increase the freedom of our optimizer, we get each time even more different surface. And that means that with different surface, we can reach similar results. Sorry, just have to take some water. Okay, now it's better. So then we move to our numerical framework, and we first of all conducted a mesh sensitivity study to see if to try to discard problems from the mesh, and we used a base mesh of 256 by 256 cells, and then we multiplied by a factor of 2 and 4. The results were very similar for the three meshes, and we then selected the intermediate mesh with n equal to 2. So this is our surface. So in the first case, we put everything together in clusters. So we have all the H1, all the asperities with H1 together, then H2, then H3, and then the additional asperities. Here just a close-up to see the mesh. So here we have in blue our traction field. So it means that our asperities are already in contact. And we can see that the mesh is pretty decent for all asperities. Okay. Then we conducted another study that was to study the influence of asperities interaction, to see if we have different configurations in our surface, if it will affect the results. So we made 100 simulations with randomly random positions. As we can see here, these are all our simulations, all of our surfaces, and the results show a really small standard deviation. So we can assume that there is, for this example, there was no big difference in the disposition of the asperities. Okay, then we move to the original targets, the targets proposed in the paper. So here we have our optimization setup. Once again, composite evasion, 256 iterations, and the same loss tolerance. Here the bounds for the different strategies for optimization. And here we have our results. So here we have the table with the heights and the number of asperities. And we can see once again that we have, Okay, we can see here that once again we have different response, but all are really close to the target points. And this different response can also be seen here to this difference in heights and also difference in number of asperities. Okay, so once again, different optimization strategies led to different surface, but with equal performance. Now I'll show, I have this little video where here we will progress in our curve. At the same time, we will progress for each strategy. So in the upper row, we have the results for the sequential optimization, and in the lower row, the results for the simultaneous optimization. On the left-hand side, we have the results for the fixed heights, and on the right-hand side, we have the results for the free heights. So as we go on, we reach the first point, and we have in the first two, by restriction, we know that only the first level should be in contact, but with the simultaneous, we already have the first and the second level in contact. Then we continue to move on. And here at the second point, we can see already the difference between the first and the second. In the upper row, we can see that the first, the number of asperities of the second level is smaller, but the height of the asperities is greater, while in the second, they are smaller asperities, but with a greater number. But in the end, they reach the same value of contact area. And in the end, we have all asperities in contact. Okay, then we try to extend this work to more sets of target points. So we generated our 81 sets of target points using the analytical model. These are the bounds that we used. And here we have the original points, the original targets in red, and in blue we have the different sets that were generated, and that blue bound is basically the different curves of pressure versus area that we obtain. So these are, once again, the parameters used for the optimization. And here we have the results in the upper row for the sequential optimization with free heights. In the lower row, we have the results for the simultaneous optimization. So we can see here that on the left, this gives showing that the target points and our responses, and we can see that for almost all of the cases, we could get good results. And on the right-hand side, we have more quantitative results with the median loss, the best loss, and the worst loss. And we can see that in the upper row for the sequential optimization, we have a loss of around the order of magnitude of -7, and in the lower row, we have a loss of order of magnitude of -6. So they are very good results. However, the main difference is in the time, an average time of optimization for each strategy. So for the first one, it took in average 10 minutes and 11 seconds, while for the simultaneous one, it took in average 65 minutes and 90 seconds. So it's a huge difference, which make us realize that for this case, the sequential optimization was more efficient. Okay, so we move on to another studies. We try to do a scalability study where we increase the number of parameters for the same target points. Instead of only optimizing the height and the number of asperities, we try also to optimize the radius, first only considering one radius and then 3 radius, one for each level. And these are the bounds of our parameters, and these are the results. So here we have the loss for the function calls, and then we have the time for the function calls. As we can see, we have here in blue the results for height, number of asperities in radius, and the results are very similar in loss to the one with only heights and number of asperities. But when we look at the time, as we increase the number of variables, we are increasing a lot the time. Okay, and our final study was just a quick comparison of different optimizers that were available on the software. So in blue, we have the arithmetic optimization algorithm. In orange, we have the standard Bayesian. In green, the composite Bayesian. In red, the direct method. In purple, the random search. In brown, we have SPCA, and in pink, we have the SPCA and Adam. And we have the median loss, the median results for loss, and we also have the standard deviation for each method. So, as we can see, the composite Bayesian, the green curve, is the one that obtains the best results for the same function calls. However, when you look at the time, as the simulations that we are performing are really quick and it's not that expensive to evaluate, we can see that the direct method is also a very reliable method for this case of optimization. Maybe when we increase the complexity of simulation, that won't turn out that well, but in this case, we can consider also the direct method. So as the main conclusions for our work, we can see that the combination of them with Bayesian optimization displays promising results for surface design. The sequential optimization is significantly faster than the simultaneous one. The increase of parameters alone increases the complexity, but does not necessarily compromise the quality of the results. And the composite Bayesian optimizer presents the best results among the studied optimizers. So as future works, we have to tried to apply this strategy to other surface patterns, application of this design strategy to rough surface, and extend this design strategy to adhesive and frictional behavior. Thank you very much for your attention.
Yeah, thank you for the presentation. I'm always happy to see what people do in code. I have two questions. The first one is on the complex simulations. Are you simulating a periodic box?
Yes, we are using the Polonsky-Keir algorithm. So it's only periodic, normal contact, elastic contact, yeah.
And the second one, in your presentation, you showed the effect of mesh size dependency. But it looked like all three meshes look the same.
Yeah.
You even try to go to coarser meshes?
Yeah, we already, because as the, sorry, I'm just trying to go to the plot. Okay, it won't be easy, but I'll try to answer. So as the simulation works so fast, we didn't need to go to so coarse meshes. Like it took like 1 second or 2 seconds in my computer. So we tried with 256, and we tried to see if we increased the refinement of the mesh, if the results will be better. So it was more like a qualitatively analysis. When we looked at the mesh, the rendering with the 256 was not that good, so we decided to go to the next level. And also, we had to restrict our boundaries because this effect happened when we had like really small asperities. This happened. So we had really small asperities. I don't think that the color scheme here is the best, but I can show the results afterwards. So here the asperities are really small, so we had like full contact, and we tried to avoid this. Yes. Okay. These target points. So basically, we use the analytical model, and we define these boundaries, and we just compute the curve pressure with these bounds. We just use only spaced values. So we H1 times 0.8, same thing for the parameters. So we did this, and we obtained the different curves. So basically, we should get different relationships, not only linear or. But we do this because in the first place we try with random values. Most of the trying to optimize feasible solutions. Yes. Which one? This one? Okay. Why do we have? Because Bayesian optimization doesn't scale well with a number of parameters. When we are trying only for one level, we can really get close to that level. But when we have more parameters, it's more complicated to optimize. And also, we are using the number of asperities are integer parameters, and Bayesian optimization is only for continuous variables. So we have to treat as continuous variables, and then before entering the simulation in Python, we have to trim the values. So it could also be more tricky to optimize. Thank you very much.
Yes.
Is it this one? No?
No. Actually,
Two?
refresh it. It should be in the drive. And no,
Maybe you upload it in another session? Could it be?
maybe try session 10. Like, shouldn't be, but I'm quite sure I uploaded it. So
This is, no?
tricky moment.
Maybe you upload it to one of these folders.
Do you have USB?
Nell'altro computer. Sì, sì. Ecco, non c'è.
You know the file name.
Yeah, exactly.
Yes, the file name is actually name of the conference, Remodeling Biological Media. The, it's below.
I can see if I B. Even modeling should be. Okay.
I think it's faster if I just take the USB
Maybe.
and drive, yes. Do you have one?
No. No. Hai la chiavetta, no?
Sì, la chiavetta.
Ci devi mettere anche il computer libero.
No, the talk is there. You just have to record the page.
No.
You have to synchronize.
Come?
Download, no.
No?
Try download now, maybe.
No, ma scarica tutta la cartella, quella. Di base deve essere già nessuno.
Oh, but it's synchronizing.
Yeah.
Can you right click here and do synchronize?
We have an error. Is it here? No. Okay. Dove synchronize?
No, devi farlo dalla cartella di qui. Prova a cliccare col destro sullo sfondo anche solo. Guarda se c'è sync. Refresh.
Non lo vedo là.
Last.
Ah, ok, refresh.
Patrick è sparito proprio adesso.
Vabbè.
Perché il talk è qui.
Tu lo vedi?
No.
Can you air go?
But yeah, I could airdrop, yes.
Okay, maybe.
Switch.
Yes, which is fine. So you continue until the meantime there is something.
Andare sui tre puntini.
Marco,
Yes.
possiamo cambiarlo. Faccio la mia presentazione e dopo avete come organizzato tutto.
Thank you.
Do I get a pointer?
Yeah. Is this one?
This is this one. Can I get forward and backward?
Yeah. You can even have the microphone if you want.
Good. Thank you.
Okay, thank you very much. I would like to talk about solution of frictional contact problems. And I would like to start just to fix a little bit notation with linear elasticity. So that would be our quadratic energy functional. We have an admissible set. We have an obstacle. We might have equilibrium conditions, some boundary conditions, complementarity. At the interface, maybe a friction law, right, which might be a nonlinear relation between tangential and normal, possibly displacements and tangential stresses. We have a non-penetration condition on contact pressure, so something which after the 3 days, I believe everybody knows very well. And this I can skip. And I would like to present a solution method for frictional contact problems, which is based on two aspects of frictional contact problems. And the first aspect is the fact that you are minimizing a non-smooth functional. And in the case of Coulomb friction, it's even non-convex. And the second one is that if you find a minimizer, you will always fulfill necessary first order conditions for this type of minimization problem, which might be a variational inequality or quasi-variational inequality. And what I would like to do is I would like to look at both worlds and try to develop a solution method, a multi-level method, which takes care of both sides, minimization side and, let's say, solution of a nonlinear system. And what do? I would like to minimize my elastic energy plus something non-smooth, which might be characteristic functional possibly and frictional effects. I'm doing this in the Sobolev scale. My elastic energy can also be non-convex. And I have a strongly local nonlinearity, and the strongly locality is important for me because what I will do, I will later on localize impact detection and friction law in order to improve the efficiency of my solution method. This I just wrote down in order to talk very shortly again about the duality I mentioned, because we have two structures. Yeah, we have the structure of a minimization problem, and in the case of a quadratic energy, the minimizer of your variational, the minimizer of your non-smooth problem is characterized by a variational inequality. You can write down the necessary first order conditions, which might be a variational inclusion, or if it's differentiable, which might be a nonlinear PDE. And if you have characteristic functional, maybe of your admissible set regularized by some parameter and friction may regularized by some parameter, you can again write down everything as a nonlinear equation, which either you can solve, and the same solution you will obtain basically if you also minimize nicely the non-smooth energy of your problem. And I will try to do both in order to have control over what I do. This comes from the minimization structure, and to have a fast solver, and this is going to come from the necessary first order condition. I'm going to do this in the multi-level context, and I would like to provide a slightly different view on multi-level methods, which is a little bit more based on concepts from approximation theory. You know that first convergence proofs for multi-level methods came up basically, I would say, in the 70s, 80s later on, and optimality at a certain point was proven also by using insight from approximation theory. And why so? Because multi-level in principle is doing nothing else than some kind of approximation of Fourier transformation. You decompose the function you would like to approximate, you would like to compute in some high frequency, medium frequency, and low frequency part. And for each of these parts, you have fast solution methods available. You plug everything together, and then you go. If you look from the approximation theory point of view, what does it mean? It basically means multigrid is replacing computation by approximation. Why so? Because you say, I write my solution on the finest level by itself minus some coarse approximation. That's a difference. And the coarse approximation itself. That's a quite trivial equality. And then you say this coarse approximation comes from the coarser level. And then you notice that certain numerical methods, Jacobi, Gauss-Seidel, CG, what we call smoothers, allow you to approximate this difference easily. And then all what remains is to compute this coarse level correction, and this you do on coarser level. So you replace basically, or how can I say, you look at the kernel of your iterative method, and in this one you can approximate very well using a coarse space. So then what you do is you need to choose a coarse approximation space. You need to find an approximation of your fine level solution in this, and you might need some energy on this coarse space in order to find a minimization problem and in order to compute your coarse representation. That works super well in the linear case, but how does it work in the nonlinear case? Right? If you have contact constraints, if you have friction, which are local constraints, which basically can only be represented well in your fine space, yeah? What is friction on a very coarse element if you have like 10 contact nodes in this element? And so the question is, how do you build your multi-level hierarchy? And I would like to give a very, in a certain sense, simple answer to this. And the answer is simple: whatever I cannot represent on coarse meshes, I just remove. And now you have to be careful, because you could say, my first idea for decomposing is to remove the whole contact boundary from my coarse level. So it doesn't disturb me anymore. I solve a nonlinear problem on the contact boundary. And for the rest, in case of linear elasticity, the bulk whatsoever, I solve linear elastic. You can do it, but it's not very efficient. So what you have to do actually, and this is what I would like to talk about, you have to first localize by discretization your non-smooth effects at the boundary. And then technically I take a point block smoother. This is basically the nonlinear Gauss seidel, which was presented this morning, extended to friction. And then in order to do your coarse level projection, you remove the degrees of freedom which you have identified to be in contact or to be sticky nodes. Sliding nodes might still be fine. You remove them from your linear system. And then you build an approximation space which allows you to approximate very well the remaining part of the solution. And you need to find the corresponding energy for this. Now, what's the difficulty? The difficulty is basically if you look at this cylinder, which is, let's say, below a curved obstacle and which want to rotate. So then what you need, if you are not allowed to go in normal direction here, what you would need in order to get a good approximation of the remaining degrees of freedom basically is a rotation along this obstacle, right? If you're not allowed to go in the local coordinate system, in this direction, this direction, this direction, this direction, what remains is sliding along the contact boundary. If you take a standard coarse level correction for multi-wheel, which is linear, the degrees of freedom or the coarse level correction would just be a push, basically, of this contact boundary part into one direction. You wouldn't rotate, you would just move in direction, whatever your coarse level correction is. So you need something, you need a basis which allows you to describe this type of rotation with a single degree of freedom. This you can build by creating linear combinations of fine level basis functions. It's a little bit of a subtle process by looking at the local normal tangential coordinate system, and this is ingredient number one, that you find a basis which allows for tangential displacement without influencing the constraints in normal direction. And this picture I'm showing to explain the influence of a bad choice of coarse level approximation spaces on the convergence piece of a multi-level method. So what you see here is 1, 2, 3, 4 different multi-level methods with 4 different choices of coarse level spaces. For all of them, we can show convergence, but they all show different convergence speeds. And this here is somehow the best one, which allows for tangential sliding. That would be a standard multi-level basis, and these are somehow mixed forms. So it's not sufficient to have something which allows you to converge to the solution. You also would like to have efficiency, and this very much depends on the construction of your coarse level basis. So we go for this one here, which seems to be the best choice. We have been doing this just as a short example for biphasic material. So that's a saddle point problem. And as a second example, we have been considering geometries like this, where you have been doing two-body contact. And what I also would like to show this maybe, let me go back. This is rough contact. Why do I show this? This is, by the way, Swiss rock from the Swiss mountains. We have put in the laboratory. And this is interesting because you have really a rough surface and need a high resolution mesh. And for high resolution mesh, you need a fast solver, right? Because otherwise in 3D, you're not able to solve a contact problem efficiently. So that's somehow the comparison of our simulations with measurements, which will have been done at ETH in a laboratory. And if you drive this to the extreme, this is what you call rough contact. So this is really a rough surface like a street in contact with, in here case, a quadratic tire. And what we have been doing, we have been resolving by adaptive refinement our mesh really up to the resolution of the roughness of the street. And here you really need a fast solver. And then what you can do is you can simulate rough contact, so high resolution on the micrometer scale basically. And what you see here is the true contact area in this particular case, which depending on the pressure you put might be something like 20%. Yeah, so I always say next time you drive with your car on the highway, please keep in mind the contact area is not what you see. Yeah, it's very, very, very smaller. Okay, so this requires a fast solution method, and this is our parallel efficiency. And I would like to talk about a little bit, this we can skip, about friction. And this is Coulomb friction. This is something we have seen already several times. So we have our friction coefficients, we have our sticky notes, right? If the tangential force is below the critical threshold. And then if we are on our sliding surface, then somehow tangential movement will be opposite to the tangential stresses, but keeping these numbers here equal. What is interesting, if you replace, we also had a remark, I believe, in the very first talk, right? If you replace the normal stresses of the solution by prescribed normal stresses, you get a convex functional. This is what people call Tresca friction. And then this friction functional becomes nicely convex, non-smooth, but resulting problem is easy to minimize. We don't do this. We keep it the way it is for Coulomb friction, and this is our friction functional, which corresponds exactly to this Coulomb law of friction. And what you can do as a very approach I do not recommend, but what you can do is you can fix a certain normal stress. You can solve the corresponding convex minimization problem for tangential stresses and displacements. Then you can insert normal stresses again, so you can do a fixed point iteration in normal stresses and can try to compute the solution of the problem with Coulomb friction. I'm going to do this slightly differently, and I first would like to talk about localization. And Coulomb friction is a local law. Basically, it's a one-dimensional law, and we apply it in a multi-dimensional context. So what do we do? First, what you need is you need your forces, your normal and tangential stresses, and this we take based on Green's formula on the residual. Okay, this is basically some kind of discretization of h to the minus 1/2 as a suitable multiplier, would be a bi-orthogonal one. Then you compute the linear residual for a certain basis function, so you simply look at a single row of your stiffness matrix, and then you can compute your normal stresses, and you can write down also discrete frictional energy, taking pointwise residuum and tangential displacements for all points on the contact boundary. So we localize by discretization. We know that our scaled residual is basically our Lagrangian multiplier or our normal and tangential stresses. And we have completely localized complementarity and friction law by discretization. Okay, this is what you do. And then what I do is very simple. I just do nonlinear Gauss-Seidel, and at each node, I solve a frictional contact problem, which is 3 by 3 and looks basically like this. And there's two possibilities. So what I do first is I'm just imagining it would be a sticky node. In this case, I know the displacements. And then I check whether it fulfills the friction law. If yes, I'm done. I have identified a sticky node. If not, I know that this tangential displacement is different from 0. This term is well defined, and I solve a nonlinear system to compute the sliding direction, basically. And since I know that the solution of my local variational inclusion is unique, I'm done, basically. Okay, so I do this for each point, and I do this in nonlinear Gauss-Seidel fashion at each unknown. Then the question is, how do I do a coarse level correction? And what I do now is very simple. The sticky nodes I remove because I know which displacement they have, right? They are sitting on the obstacle and don't move in tangential direction. A sliding node still has a certain amount of freedom. At least it can move as long as it does not become a sticky node. Yeah, so this is what it can do in tangential direction. And so what I do is I remove all these degrees of freedom, and for the remaining degrees of freedom, I just make a Newton linearization. Okay, so that's constraint linearization because I know on a certain subset I'm differentiable. So this I do. I compute second derivative and some correction terms, which I simply add to my to my quadratic approximation of my energy functional. And if my energy functional is quadratic, that's the energy functional itself. Then you can prove if you have a certain condition on your coarse level correction. So basically, if you don't change regime from sliding to stick, then minimization of this coarse level energy will also imply minimization on the fine level energy. So this is consistent. Whatever you do on the coarse level energy will help you to solve your frictional contact problem. And this is what I just said. And if you do this, if you implement it, it works very nicely. And this here is, I did this on a laptop some time ago, so this is why I only went up to 1 million unknowns. But if you look here, this is number of nodes, this is number of degrees of freedom, and this is solution time, and this is for a frictional contact problem. And as you see nice scalability. So basically, what you get is always a factor of 8, which corresponds to the uniform refinement I have been doing. So I can solve a frictional contact problem with a multi-level method, basically scalable, and with multi-grid efficiency, and overhead for this additional linearizations is in the order for this particular problem of like 30%. This is a tire, a torus pressed on an obstacle. These are the tangential stresses. And it's not so easy to compute. Yeah, if you look for Hertzian contact problem for normal stresses, right, this parabolic shape you get quite nicely. But here you see sticky zone, yeah, until you reach critical stress, then you see sliding zone, and then it goes back. It's not so easy to get this shape of the tangential stress nicely and well. What I do also is I take care of the friction in Gauss-Seidel fashion. So I talked about the Tresca friction and about the fixed point iteration in normal stresses. I don't do this because what you can actually prove is that this fixed point iteration is a contraction rate which degenerates, which mesh refinement. And so what we do is at each node, as you do in Gauss-Seidel, we also take all the information we have from the previous degrees of freedom. And if you do this kind of nonlinear Gauss-Seidel in your non-convex friction functional, you get a very good scalability in terms of number of iterations for refining mesh. So this is not 100%, you see a slight increase, but quite robust in terms of mesh refinement for frictional contact. How much time do I have left? 2 minutes, okay, super. So then I have 2 minutes to talk very shortly on how to parallelize. Yeah, because you would like to parallelize. How do you parallelize? You decompose. And what you see here is how this solver works when you parallelize it up to 16 million unknowns. That's number of iterations, which stays stable. And there's one thing I would like to mention, and this is usually when you do parallelization, you decompose your problem, and then you might have an interface between two subdomains with overlap or not overlap. And what you do is at the interface, you usually take maybe linear combinations of the values on the different subdomains in order to synchronize. You cannot do this in a frictional contact problem. Yeah, because if on subdomain A you have found a sticky node, and subdomain B you have found a sliding node, please, what is mean value of sticky and sliding node? So I follow a dual approach. I synchronize simply the stresses. Yeah, I take mean value of the stresses, and then I loop again over the boundary between the processes, and for the given stresses, I solve again my local variation inequalities, which then on each processor independently will give rise to the same result. So that's the synchronization you need to do. And then just 2 pictures in order to get a little bit more of efficiency. This is adaptivity. So this is nice impact of this pyramid into an elastic structure. So this is an error estimator we have designed particularly for contact problem, taking into account exactly normal stresses developed at the contact boundary. And as a last argument, I just would like to show that the idea of decomposing into local nonlinearities can also be done on a slightly larger scale, which is nonlinear domain decomposition. Right, you can decompose your domain into subdomains, and on each of the subdomains you solve independent nonlinear subproblems. You plug everything together. You need the right control strategy. We are using trust region, and then you can build nonlinear domain decomposition, which is way more efficient than a standard trust region method would be. Nonlinear Gauss-Seidel does nonlinear domain decomposition basically with 1 point or 3-dimensional subspaces, and you can do it also with slightly larger subspaces if you wish. Thanks a lot.
Just to make one thing clear, because you state the problem at the beginning as a minimum problem of J plus P, and when then you consider no friction with phi given by the formula you put there, but it's not a minimum problem in that case. I mean,
no, it's non-convex. It's non-convex minimization. It's a non-convex functional.
Yeah, but the minimizer will not fulfill the equation that you.
No. This was for the regularized case, and this was for the other functional I wrote. Yeah. But I'm following the minimization structure in my approach. It's basically, I mean, the method is, how can I say, is motivated by a linear solution method, but de facto it's a multi-level minimization method. That's the point. I use my coarse meshes as additional search directions to find the minimizer. This is an extended. Which which threshold?
Your sigma n of u, you update it, because otherwise it won't be any.
Yeah, but this I update iteratively. This is updated in Gauss-Seidel fashion. This is updated iteratively. Yeah, you have to, yeah. Otherwise you will never converge, yeah.
I will ask you a question.
Thank you very much. Maybe I misunderstood, but at the coarse scale, let's say you find a node that is sticky, and then use a multi-grid, you go down in scale, you say in this region that's now refined, you still sticking, it's remain sticky in the zone. I think that's what you said. Or I misunderstood.
I said if I find a node which is sticky, I remove it from the degrees of freedom, and I make my coarse level correction only on the other degrees of freedom.
Okay, so then my question is, could it be that at the coarse scale, one region that you think is sticking, if you were to zoom in and add some fractal roughness and look at the smaller scale, that you will find some patches in there that could be, in fact, slipping?
I mean, the stick slip detection is completely done on the fine level.
But you have to search on the coarse.
I search stick slip on the fine level. I identify my active set. I remove stick and sticky nodes. I do my coarse level correction. I give a correction back, and then I do it again. That's the idea. So because the coarse level cannot represent all these stick and slip zones. Yes, I keep all the non-linearities on the fine scale. Coarse level are completely linear. Everything difficult is removed from the coarse level. Yeah, the trick is only how to remove. Yeah, that's all.